Hi, I'm Richard Chopping. I'm the manager for Geoscience mapping through cover here at the Geological Survey of Western Australia. In this talk, I'll be taking you through a very general overview of some aspects as to how physical properties are changed by mineralizing processes, and in turn, how these changes might affect various geophysical responses. Before we begin, it's important to go through some acknowledgements. This presentation is built off work throughout my career, including work that has contributed to 3 very important geoscience-related cooperative research centres. Some of the data used in this presentation were contributions to these CRCs by Goldfields, Barrick and AngloGold Ashanti. There are also a number of people I've collaborated with on this research. Their contributions are acknowledged for helping us advance the science as to how we understand the changes in physical properties due to chemical alteration within mineral systems, and in turn, how these changes affect geophysical responses. I'm certainly not the only person to have looked at this topic. Today's webinar is aimed especially at geologists to open people's minds to the concepts and ways in which we might hope to be able to map some of the changes due to alteration systems in geophysical data. In that vein, I've made this a very general talk. I only go through some very basic mathematical and geophysical concepts. I will say that once you look at some of the aspects around rock physics models and some of the complexities within, there are a lot of aspects that need to be considered that I won't be covering in today's talk. It's also important to be very mindful of what geophysics can resolve, but also what we cannot hope to resolve with geophysics. Ultimately, however, most ore bodies are hosted in basement terrains with rocks which have predominantly had most of their pore space closed, at least at a geophysical scale. So to first order, a number of the approximations that I make within this talk are still valid for such systems. After explaining some broad concepts around some of these changes that you might expect in physical properties due to chemical alteration within mineral systems, I'll take us through some case studies of the Yilgarn Craton. In this craton, the orogenic gold systems present give us a really great opportunity to examine some of the changes in physical properties due to alteration systems. I'll also take then a theoretical look from a geochemical perspective as we simulate the formation of ore bodies and then predict the geophysical responses of these ore bodies. I'll also take the audience through some of the pitfalls and things people must consider when working on a topic such as this. Finally, and to round out this presentation, I'll talk about the future and GSWA's renewed focus on physical properties and how this will help us as we start to map the terrains out in the undercover regions of Western Australia. To begin this talk, I want everyone in the audience to cast their minds back to first year geology. In particular, I want the audience to think of first year practicals aimed at mineral identification. This is one of the absolute foundation skills of geology. It's a key formative skill for budding geologists. It's important to be able to learn the diagnostic properties of various minerals. The classic and sort of first mineral you learn to identify is the hardness of quartz, being harder even than most knife blades. On the other hand, a clay such as kaolinite is very distinctively soft. Also, comedically for first year students, it sticks to your tongue when you place it on your tongue. A really diagnostic property of another mineral is the very distinctively red streak of hematite. A property in terms of the way that the crystals are formed is the one perfect planar cleavage of the micas such as muscovite illustrated here. Another diagnostic property is luster. A mineral sulfide such as galena has a very metallic, distinctive luster. On the other hand, another sulfide, sphalerite, actually features a very obvious resinous luster. But if we zero in on those two sulfides, there are other properties we might not realise that are actually diagnostic. Galena in particular is very heavy, even amongst the sulfides, for its size. This relates to the density of galena, which then in turn would relate to the gravity response of something like galena. The other one that's very unique and most people don't realise is that sphalerite doesn't just have the resinous texture, it is also non-conductive. unique amongst the sulfides in this property. If you were to actually measure its electrical resistivity, you would discover that it would not conduct electricity, whereas the other sulfides will. So these properties can be diagnostic and can help us to interpret data sets in terms of some of the changes. This is a classic chart for those who are familiar with seeing geophysical responses of things relating to electrical conductivity, such as magnetotellurics or electromagnetism. This chart sort of illustrates conductive materials on the left of the chart and resistive materials on the right, and also relates to the classic rainbow colour scheme most people would have seen conductivity models presented as. We can also place those two minerals I just discussed in terms of their resistivity/conductivity aspects and where they would fit. So sphalerite being non-conductive would sit far over to the right, and galena being conductive would fit more over to the left in terms of this properties. One of the challenges, however, I won't be talking about conductivity too much in this, is that conductivity is a much more challenging property to be able to do some averaging to understand some of the changes, and there's a lot of other complexities that come into it. So in this talk I won't actually be focusing too much on conductivity, but it is a very important property for us to consider, especially given the ubiquity and increasing ubiquity of electromagnetic sensing techniques or even magnetotellurics. When people think of regional geophysical datasets, the first and primary dataset most people would think of is magnetic data. On this graph, I've actually got magnetic susceptibility, which is the ability for a mineral to have a magnetic field induced within it through the magnetic susceptibility. So I've plotted that on the y-axis. On the x-axis, I've actually got a temperature at which that relationship falls down, the Curie or Néel temperature, where they cease to be magnetic. Magnetite, very magnetic mineral, but other minerals such as pyrrhotite or ilmenite are variably magnetic, and that weak magnetism is a diagnostic property even in hand specimens, and most geologists might be a little bit familiar with that. But if you were to interpret magnetic data sets, you really are interpreting the distribution of a few magnetic minerals. The other data set that I think is very important is to actually think about gravity, but also seismic velocity, and increasingly we are thinking about seismic velocity. And rather than just plotting these individually, I thought I'd actually plot them together, and this is a number of different minerals, or different mixtures of minerals, plotted up in terms of seismic velocity on the y-axis against density on the x-axis, and some of the different properties. There are also some interesting trends. I'm not going to go too much into some of these relationships. Most people would be familiar with the idea that you can relate density to seismic velocity, but that relationship will actually vary according to the rocks that you're within. This red line shows the sort of thing you might expect for sort of sedimentary rocks. As you start to close pore space, you actually increase the seismic velocity much faster than you increase the density, and then you start to go through some of the key rock forming minerals and increase the seismic velocity and density in this sort of relationship. As you start to think about more metamorphosed rocks, you might actually follow this green line instead, where you actually increase seismic velocity less rapidly than you increase density. And finally, some of the sulfides actually plot with very low seismic velocities given their densities. And as I said, things like galena actually plot way off to the right of this chart. They are that much denser than standard rocks. So you might well expect that we might be able to see some of these changes from these different minerals once you change the proportion of those minerals through processes such as chemical alteration as you pass fluids and higher temperatures through an area and you form ore bodies, and the more distal alteration packages to alteration systems. Ultimately, however, no matter how fancy the rocks are, such as these couple of photographs from around the GSWA office, no matter the fancy texture of the rocks or anything, the properties predominantly come from the minerals within. So no matter the fanciness, ultimately a rock is just a collection of minerals. So rather than trying to do that in detail on a very fancy real rock, we'll have a geophysicist's rock. And we'll break down the three properties. The symbol ρ stands for density, K being the magnetic susceptibility, and Vp being the P-wave seismic velocity, the key seismic velocity most people think of. You can actually relate all of these properties to some kind of linear weighted average of the properties. Seismic velocity requires some extra tweaks in certain environments. Density is absolutely a linear average, and for low enough amounts of magnetite or magnetite equivalent, magnetic susceptibility is also just an average of the properties within the rock. So even though rocks look to be very fancy in terms of the minerals within them, ultimately you can understand their properties through the proportions of the constituent minerals and also the properties of those minerals. To illustrate this, I'm actually going to take us through some case studies within the Yilgarn Craton, a very important gold hosting area, and zeroing in a little bit, the eastern goldfields, very rich in terms of gold, and we'll focus on two sort of key areas, one around the Kambalda region and the Snives gold mine, and we'll focus on a couple of mines up around the Laverton area being Wallaby and Sunrise Dam. We'll first turn our attention to Snives, and what I've got here are two graphs. Density is along the x-axis for both. The left-hand graph we have seismic velocity on the y-axis for the left-hand graph, and for the right-hand graph we've actually got magnetic susceptibility. It's in a logarithmic scale, that's just because these are very large numbers and it's a much easier way to represent it. This is just wireline data for one particular part of the stratigraphic package for this one particular drill hole. Within this drill hole, I've looked, it's about a 1 kilometre deep drill hole, and I've pulled out just this one particular unit, and I'm highlighting the relationship between these three very important properties. I've also coloured two important intervals, just simply to illustrate some of the changes, and you can see most properties plot within a very restricted field. So that's demonstrated by these dashed ellipses. Even so, there are some other properties which are trending off in a different direction. If you imagine a property at the apex of that ellipse, as you gradually add pyrrhotite to that mix and you transform the properties from the original rock through to the rock containing more and more increasing amounts of pyrrhotite, you follow a linear line, the straight line on that left-hand graph. On the right-hand graph, the bent curve is actually what a straight line looks like in a log plot. These are both linear trends. And you will actually see that the top and the bottom of the ellipse, drawing lines from those to define a cone with the apex at the mineral that these things are being altered to. And we can see that these two very important intersections are trending towards the properties for pyrrhotite. It's probably a mix of other properties within there. And also what I'm showing is only on the right-hand graph around magnetic susceptibility, I'm only considering the magnetic form of pyrrhotite. This is probably a case where you're actually dealing with either a mixture of the two, or there might be some quartz or some other things involved in terms of this vein that we've intersected. But we can clearly see there is a trend towards a very key alteration diagnostic mineral in pyrrhotite, and this ultimately tells us something about the redox conditions and the alteration that's occurring. We can also see how much that's changing the physical properties. You're getting a much larger density response. These are very small intersections, and this was not necessarily a mineralized hole, it was just a vaguely altered hole. But even so, we're around 4 kilometers away from a very large deposit, we're still seeing a key alteration trend highlighted in the physical properties. The same is true when we turn our attention to a different unit. This was in the drill logging, this was just put in as an intermediate rock. It's probably a bit more of a altered package. And within it were actually highlighted areas in which geologists noted either a little bit of pyrite or a little bit of pyrrhotite relating to two different alteration phases within the mineral system. And I've highlighted those two things, and I've also highlighted a 1 meter interval in these black diamonds as well, and I'll talk about that in a moment. So again, we can see that most of the properties plot within this field. So most things of this intermediate unit you could infer are sort of plotting in this area in terms of seismic velocity and density. If we then take that alteration cone concept and we start to look at things trending towards pyrite, we can absolutely see that trend out towards pyrite from those samples. And equally well, we can see in the light pink purple colour the trend out towards pyrrhotite as well. The final one in terms of that vein is actually where a vein of quartz, pyrrhotite and muscovite essentially was intersected. But the important properties here is both the muscovite and the pyrrhotite. And you can actually see that drawing a line between the two, there is a cone that sort of, the apex of that says there is some mixture between those two. The mixture involving quartz would actually involve a mixture within the restricted field that you sort of see the general properties within. So again, we can definitively see even these veins, we have significant changes due to chemical alteration within the mineral system. And there's really two key takeaway points that I want people to take from this example from the St Ives. Alteration clearly changes physical properties, and this is true even for areas in which we're distal to a deposit. This was not a drill hole that intersected any significant mineralization, it just intersected some of the more distal alteration packages, and we're able to see the changes due to those physical property changes of the minerals within those key alteration phases. Ultimately, those changes are entirely consistent with the property of alteration minerals. So if we start to consider the alteration minerals and then the properties, we can start to infer some of the ways this would change different host rocks as we alter them. This is also something which is highlighted now we turn our attention to Laverton. I'm just showing up box and whisker plots. Again, density, seismic velocity, like to mix it up so people get different ways of looking at data. These are different alteration phases and how they're arranged. Ultimately, the ones at the top of the graph, which are coloured with a sort of yellow gold colour, they are the ones which are alteration phases containing gold. What you can actually see is that the samples containing gold have variable seismic velocity, but they absolutely have a lower density than you expect for the phases that do not contain gold. And that actually comes down to the alteration facies. Once you're talking about gold, you have a little bit more quartz and some other things coming in along with gold, whereas the other more distal alteration packages are actually more associated with denser minerals. And that's something that is very important for us to be able to understand. So you're not necessarily looking, if you wanted to target the gold, for the density anomaly. That would give you more of the distal alteration packages. The more proximal alteration package where the gold is would actually be slightly lower density and hence slightly lower gravity response. Things become a little bit harder once you start to look at hand specimen results, because you need to start to take into account the fact that hand specimens do just have a fabric within them, even just microfractures, and those microfractures can affect hand specimen velocities. But even so, we do have a number of different properties that plot up, and there are significant changes which result from some of the alteration packages here at Wallaby. But to think about the importance of fabric, I thought it'd actually be really good to go back to that picture of muscovite and the planar sheets. On the left, I've tried to draw the three-dimensional aspect around the seismic anisotropy of muscovite. So that is the ways in which seismic velocity is slower versus faster. It's much slower perpendicular to the fabric on the single cleavage plane of the muscovite compared to the seismic velocity along those cleavage planes. And that fabric does persist not just from the single cleavage plane of micas, but also due to fabrics coming from structural changes and structurally hosted ore bodies such as these orogenic gold deposits. So turning our attention to Sunrise Dam, also near Laverton, we're able to take some specimens, start to look at them and note the fabric within them. And this fabric is developed parallel or perpendicular, according to the different axes that we're looking at, to the shear zone. And on the right, I'm actually showing seismic velocity with relationship to pressure. So these were put into a high pressure apparatus and pressure was applied to them. There are small scale fractures within these samples, and those fractures first close up, which actually increases the seismic velocity quite rapidly. As you start to get higher confining pressures, much closer to those pressures you would experience, those rocks would experience within the crust, you start to see more of the seismic velocity, which is the overall bulk seismic velocity of this sample. The interesting aspect about this and how this matters in terms of imaging some of these alteration systems is we need to actually consider that fabric. And ultimately, when you start to look at these things, we do have a trend as we start to get to both some different lithologies and some different alteration phases. The fabric also starts to matter. The shear zone is thick enough that you can see this in seismic, and we need to think about the vertically incident seismic wave that comes in to give you seismic reflections. Ultimately, this anisotropy means that as you change the dip of the shear zone, you actually change what is called the reflection coefficient, which is the ability for an interface to reflect seismic waves. What I've shown on here are some dashed lines which sort of would give you a weak to moderately strong reflection. Ultimately, the challenge here is if the shear zone is vertical, it would present the ability to get a reflection. However, a vertical shear zone would not give a reflection in a seismic section, whereas if the shear zone is perfectly flat, it starts to have properties much closer to the properties of the background, and you wouldn't actually be able to see it. So the fabric's very important, and it just happens that the sunrise shear has a nice Goldilocks dip, if you like, where it's able to be imaged in the seismic data. And this is shown in terms of some mine-scale seismic. You can actually start to see these shear zones, and these shear zones are absolutely coming from the minerals formed within that fabric, as well as the fabric itself. And essentially that provides you the reflection. So the takeaway points for the examples from Laverton that I've just provided, mineralogy absolutely is a primary control on physical properties, and that's something we need to consider when we start to think about these systems and how we might be able to see them in terms of their physical property and their geophysical responses. One definitely needs to consider fabric, at least on one level, about the changes in the orientation, and we need to be able to see that and understand that in order to interpret geophysical survey results. To take out some of the complexity of some of these fabric aspects, but also to more easily understand them, we'll now turn our attention to a simulation, very simple simulation of how some of these orogenic gold deposits form, with a fault, an interface between both some more felsic and some more mafic rocks, and some fluids coming from an intrusion at depth. And essentially running these simulations, which simulate about 1 million years worth of geological history, at the start that architecture represents the architecture of the rocks and what you expect if there isn't an alteration system present. And that's what I'm showing on the left. There's actually a number of different minerals within it. In fact, there's 23 minerals that were simulated to provide us the unaltered architecture. Once the alteration is run through and we've simulated 1 million years worth of geological history, we've actually got 33 minerals, and we can use all of those minerals and the averaging that we've talked about to simulate the properties of this distribution of alteration, but also primary lithology. So what I'm showing on the left is the density, on the right the magnetic susceptibility, so relating to gravity and magnetic data. And at the bottom of those two, I'm actually showing the changes due to chemical alteration. So the important aspect here is the ore body actually forms roughly in the middle of this model. And you can actually see that much lower density in the middle of the model, and that lower density is exactly what we saw at Wallaby, where we had the gold bearing alteration phases were actually lower density than we might necessarily expect. On the flip side, there is almost no magnetic response, but there is some magnetic response along the fault, where you've got a little bit of increased magnetization along the fault. The other aspect is most gold deposits are not found at 7.5 kilometers depth. They are found where they're very close to cropping out. So if you cut the top of the model off, you're effectively simulating all of the history of the uplift and erosion of these terrains. So from that, we can actually start to simulate the geophysical responses of these terrains and simulate what these things might look like once you run them. So in the top, I've got a section which is essentially simulating how we form the gold deposit, and we get the broad architecture of the slightly higher gravity response to the left-hand side of the profile, where you've got a bit more an increasing thickness of some greenstone, slight decrease because of the fault, and then you've got the more felsic, nice basement happening off to the right-hand side. In the bottom section labelled B, where I've got the circle, is where the main gold body forms, and what I've then got in C is the difference in those two profiles. And you can see the red line, which is after alteration. There is actually an increase in response off to the left-hand side of where the gold deposit is formed in this simulation. But directly over the top of the gold deposit is a slight decrease. And that slight decrease is at the level that a gravity survey could see. The other part about these kind of simulations is you can start to look at these and start to ask the question is what happens if the deposit is fully eroded, and in fact you would still see the higher gravity response off to the left-hand side of the ore body. But once you start to talk about buried deposits, and in this case they're either at the surface, 500 metres buried or eroded, or a kilometre of burial or erosion, you actually still have that strong response of the slightly lower gravity response than you expect directly over the gold deposit. And this persists even after you haven't fully exhumed the deposit. So if you search for a deposit like this, you are looking for anomalies which are a little bit lower than you expect. But they're still in an area where the gravity response is moderately high. So it might actually look quite boring to you, and it's something that you need to do a bit more modelling to tease out the difference compared to what you expect for an unaltered architecture versus what you're actually seeing in the results. And the takeaways that I want the audience to take from this area around simulations is that there are considerable changes in physical properties that are seen in alteration. We saw that in the hand specimens. We can also see that in the geochemical modelling. These changes are not just appreciable in terms of small scale things that you can see in terms of theoretical physical property responses. They are also significant at the scale of geophysical surveys. The other aspect is we have to be very careful about what we mean by unaltered material. We might be looking at things that are unaltered, or we think are unaltered, but they actually represent the more distal alteration phases. So we need to be very careful about that, because ultimately any geophysical anomaly is only as good as what you think it is anomalous compared to. So you do need to think about that at all stages that you're trying to interpret more of the mineral systems component into geophysical data set interpretation. So now I want to turn to a caution on geophysical modelling. So obviously people think that geophysicists provide them truth, and we think we do, but ultimately there are a huge amount of uncertainties on any aspect of geophysical data and then the interpretation of it. So let's just take theoretically an observed profile such as this red line. We might have some idea from architecture from, let's say, seismic reflection or something else. We have a bit of an idea of the architecture, and this is sort of what we're looking at. And we go and we grab a book and we sort of throw in the properties of what we expect for some greenstones and some gneisses and those kind of things to give you the basement, and we think we've got a granite at the bottom and it's got a lower density than everything else, and we've got a fault with a much lower density. So we throw that in. And then we calculate the forward model and we get this black line. So the classic thing here is then geophysicists, or under the guise of geologists, looking at this, going, oh cool, it doesn't fit, let's start changing some things. So you make your greenstone a bit thicker, you will change the density that little bit just to sort of help everything out. Might add a little hump on top of your granite in terms of a way to explain why you're getting slightly lower response than you expect in that area. And you put these things in and you'll calculate it and you'll absolutely see it. But as I've just demonstrated, this can also be the result of the formation of a gold deposit, because we haven't even considered the possibility of looking for that gold deposit. We can't see it. In this section, with this kind of modelling, we have no signature that there is actually a gold deposit in these data. And it's something we need to be very mindful of. We cannot see something that we are not looking for. Until you are open to the concept around some of these changes and things not just being related to primary lithology, you may not necessarily even see the possibility of interpreting it in your geophysical data. And that's a really key aspect. The other key aspect is it's very important for us to consider the fundamental unaltered background properties for the bulk rock before we even change things. So now we must consider, where are we off to next? So this is the state geological map for Western Australia. And ultimately, the survey exists to understand and map the Western Australian geology. Ultimately, what we're actually doing, even though we don't call it this, we are attributing Western Australia's stratigraphy. So our field observations tell us something about the different units that we can map spatially across the state. We have drill core observations that we also add into that. We have some geochemistry that gives us a huge amount of information about some of the lithological packages. We have a lot of mineralogy in terms of the things that we look at. But the other aspect that we need to be able to attribute in here are physical properties. So what do we expect for a particular unit, its physical properties to be? We've currently got on a program to acquire physical property data in a few key areas of Western Australia, and namely things around the Eucla basement, some of the drilling there, some samples from the western component of the Arunta, essentially at the crossroads of Australia, got some samples that we've measured for the Patterson and also for the Eastern Goldfields. So we already have a program where we are starting to get some of these physical property data and understand what that might mean in terms of some of the changes that might be happening due to alteration systems, but also to start to attribute the stratigraphy of Western Australia with some of these key properties so that we can start to even think about some of the areas and what things may or may not be anomalous. So in terms of today's journey that I've taken you on with this webinar, which has been a very quick look at some key components and showing you ways in which mineral systems can change the physical properties and also the geophysical responses around those mineral systems. Ultimately, if you to really understand this, you have to go back to first year geology and you have to be thinking about mineralogy, and then specifically you must be thinking about the mineralogy changes which occur due to chemical alteration within a mineral system. The other aspect you need to think about is that geophysical anomalies are only ever as good as the background you're testing them against. You need to really be thinking critically about what you think is your background that you're saying is either something as anomalous or not. Often the deposits will not be in the biggest anomaly. They may actually be in the most bland response in terms of the geophysics, and it only becomes an anomaly once you take into account the broad background architecture and physical properties before alteration. The other aspect is you may very well need to calibrate your samples because there's some changes in rock physics models which are a bit more complicated, such things as texture, or once you start to look at properties such as electrical conductivity. It certainly isn't universal, but to a first order, the responses you get result from mineralogy and the properties of those minerals. Until you're looking for them, you will not see them. And it's very important that we start to consider this as a component of how we interpret geophysical data, especially in the areas that do actually have mineral systems within them. So thank you hugely for your attention in terms of this talk and going over this very broad topic. I very much welcome people to continue the conversation. Certainly look forward to being able to address some of your questions and ways in which this will help us advance the science of us understanding especially the undercover parts of Western Australia. Thank you very much for attending.